let's get started. Suppose we wanted to divide 6.6 by 3. Let's look at that graphically. There's 6.6, and we want to divide it into 3 equal parts. To see how to do this, perhaps it would be good to express 6.6 as its mixed number equivalent. 6.6 is the same as 6 6/10. Now think about dividing 6 6/10 into 3 pieces. If we do that, we see that we can divide it into 2 2/10 and have 3 of those. That's pretty straightforward. 6.6 divided by 3 is equivalent to 6 6/10 divided by 3. And in our head, we can take the 6 divided by 3 to get 2, and 6/10 into thirds is 2/10, which is absolutely equivalent. If we divide 6.6 by 3, we get 3 pieces of 2.2. If we look at this in terms of division, it really looks like exactly the same thing as division by whole numbers, except we need to take where the decimal point is in the number we're dividing and just move that up and keep it in the same place in the number we're dividing to. As I indicated, it's exactly like regular division, and the only difference is that we need to locate the decimal point and put the decimal point immediately above it in the division symbol, and you can't go wrong. Let's look at another example. What about 18.3 divided by 9? When we start to do that, and we can treat it just as regular division, but remember to put the decimal point up above where you see it in the number you're dividing. Now let's perform the division. 9 goes into 18 twice, fair enough. We subtract the 18, and how many times does 9 go into 3? We can't do that, so remember that we can add zeros to the right of a decimal without changing the value. So in this case, to continue the division, we just do that, and now we can continue to divide, because now I'll bring down a 0. And when I do, I have 0 because I couldn't do anything with the 3, but now I can say 9 times 3, having brought the 0 down, is 27, and I find I get another 3. Bring down a 0, and I get another 27. You see what's going to happen here? I can keep going, and I get 2.033333, and I can keep dividing here until the cows come home. And it will just be from here out an infinite progression of 3s. In other words, this division, if I wanted to keep it going, would just never end. What I need to do is to decide at what level I just want to stop, or at what level I'd like to approximate. Also, when you have division expressed this way, where you have infinitely repeating decimals, there's a way mathematically that you can indicate this. It's 2.03333. In other words, it just keeps going. We have a way of notating this. We can write 2.03, and if you draw a line over that part that repeats indefinitely, as I've done here, that tells whoever is reading your math that that the 3's at that point will just keep repeating forever. Let's look at another example. Suppose I have 0.07070707, and it's not just a single digit, but 2 digits that keeps repeating. Try to guess how I'm going to write that. You got it? I put the line over the 07. So if it's a larger unit than just one number that continues that infinite sequence when I do a division, you put the line over the whole piece that repeats. Sometimes it could be 3 decimal places, then it repeats after 3. Other cases may have it repeat after 4. You need to include the whole repeating part underneath that line. And that's used to indicate a case where the decimal might be repeating. We'll use the bar over the repeating part. Let's look at another case. 9 divided into 411. We see that 9 goes 436 times. We're left with a 5. We bring down the 1. 9 times 5 is 45. Now what happens? At this point, you see, since they're both whole numbers, I now add a decimal part to the 411 that's worth nothing so that I can keep going. I changed 411, the whole number, into 411.0000, however many I might need. Then I move the decimal point above the number I'm dividing, exactly as I've done it before, and now I can go on. 9 into 60, let's try 654. Whoops, guess what? It looks like we're going to get something that repeats here again. How would we express this? 411 divided by 9 can be represented as 45.66666, where the 6 keeps repeating indefinitely. I would write that as 45.6 with a bar over it to indicate that that 6 keeps going. Well, we can get decimal equivalents and get them as remainders, and what we need to do is add 0.0000 to the dividend. So if you see a division by whole numbers that's not going to work out evenly, you can change it to decimals just by putting the decimal equivalent of 0 in, 0.0000, and you can keep it going as long as you want and then be able to do that math. You may remember that we've talked in the past that decimals can be thought of also as fractions, and we looked in some case at the decimal equivalent of fractions. Let's investigate that a little bit more in this next section. Here's 1 pi, or I guess you have to really use your imagination to think about that being a pi, but suppose we're dividing it into 2 pieces, each piece being half the pi. What's the decimal equivalent of that 1/2? Let's use what we said before to divide 1 by 2. We set it up. Now you remember that we can make a decimal out of that 1 by adding a 0.000, and let's do that. What is 1.0 divided by 2? The first thing we need to do is put the decimal point above where it is in the number we're dividing, then do the math. All of a sudden, we've already seen, that this division works well, and 1/2 is equivalent to 1 divided by 2 if you perform that operation, which gives us the decimal equivalent of 1/2 of a pi as 0.5 of a pi. Continuing our investigation, let's take the same pi, but now instead of dividing it 2 ways, we'll divide it 3 ways so that each piece is 1/3 of the whole. And of course, now you have 3 people fighting to get their 1/3 of the pi, and we'd like to express 1/3 as its decimal equivalent, and we divide 1 by 3. Writing it this way, and then extending it so that we don't change the value of the 1, but we now can continue the division process for quantities below 1. I see that 3 won't divide directly into 1, so I have to continue. I put the decimal point right above where it is in the division example and ask, how many 3's can I get out of 10? I can get 3 3's, and 3 times 3 is 9. I then subtract 1, bring down the 0, and it looks like I'm going to have a repeating decimal. And this could just keep going forever. Now I can say the decimal equivalent of 1/3 is the repeating decimal 0.33333, which I can tell people about by writing it this way, where the bar over the 3 means that it repeats indefinitely. Let's see if we can get a general rule. If we have a fraction a over b, and we want the decimal equivalent of that fraction, what we do is divide a by b, and we put in a bunch of those zeros so that we can perform the operation. When we do this, we can see that there are quickly some decimal equivalents that we can get, for example, and some of these are actually useful for you to learn. For example, it's very useful in the real world to know that 0.5 is the same as a half, or 0.25 is the same as a quarter. Also, notice something else interesting. Where we have things that are divided by 3, it looks like we get repeating decimals. And this has to do with the fact that there's no way that if you're working with 10, 3 is in no way easily divisible by 10, no matter how much you want to multiply it or fool around with it. It's useful to know these equivalents here at any rate, and perhaps from these you can work out some others. Let's look at writing mixed numbers as decimals. We have 7 and 14/15, and we would like to express that as 7 point something. Again, all we need to do is remember that 7 and 14/15 means the same thing as 7 plus 14/15. Then we change the 14/15 to a decimal by dividing 14 by 15. When we do that, we see that 14/15 is equivalent to 9.3333, and we can express 7 and 14/15 as 7.93333333333333, or just 7.93 repeating. Now let's look at dividing something with a decimal by something with a decimal. If we set this up, we have 18.43 divided by 3.4. When I'm dividing by something with a decimal in it, that's a little bit annoying. I'd like to be able to express this as an equivalent problem where I'm dividing by an integer. How can I do that? If I understand that I do the same thing to the numerator and denominator, the number I'm dividing, and the number I'm dividing by, it won't change anything. So let me multiply top and bottom of that by 10. 10 over 10 is 1. Now by multiplying by 10, the number I'm dividing by is no longer expressed with decimals. It's a 34. But when I do the division of 184.3 by 34, I can just do it the same way I did before by moving the decimal point up above, and the result is 5.4. And if I wanted to, I could just keep going here and fill in. And of course, a question is, where do you stop? And that really has to do with the problem you're given. Usually, however you're working the problem or in real life, you understand, for example, if I'm working with money, I might want to go to 3 decimal places and round it back to the nearest cent. Or often when you do problems like this, your book or your teacher will tell you how many decimal places to take it to, and then you round to that particular place. Let's look at another example. I want to do that division, but I have a 0.5 that I'm dividing by. What I need to do is multiply the 0.5 by 10, and doing that will move the decimal point, effectively move the decimal point one space to the right. But if I move that decimal point one space to the right, I need to move the decimal point in the number I'm dividing by an equivalent number of spaces, and I've changed the problem to that, where now I'm dividing by a whole number. When I do that, the result is 88.4. Let's look at another example that extends this procedure a bit. We have 76.42 divided by 37 thousandths. Let's perform this division and see what happens. What we need to do, you remember, is divide by a whole number. So we need to keep multiplying by tens until we get 37. Let's do it little by little. Multiply by 10 and the decimal point moves over 1. Multiply by 100, it moves over twice. But now you see I might be running into trouble because there's nothing after that 2. Remember that we can add a 0 at the end of a decimal and not change anything, so we'll throw another 0 in, and that allows us to move the decimal point one more place. So what we ultimately have now is the equivalent division of 37 dividing 76,420. Then we can perform that division as we normally do, and when we do that we get 2,065 and 405 thousandths. A good question might be, when do you stop? And we've talked about this before. If, for example, that were money, you might as well stop there, and then you can round the 40 up to a 0.40 up to 0.41. Often the problem will tell you how much to round to, or as I indicated before, common sense will tell you what you need to round to in terms of operating in the real world. In this case, we round, it's 2065.41 to the nearest hundredth. And often you'll find yourself rounding to the nearest hundredth when you're dealing with money, because we don't go down to thousandths at this point when we deal with currency anymore. Let's take a look now at dealing with square roots. As an example, let's play around with the square root of 10. We know that the square root of 9 is equal to 3, and the square root of 16 is equal to 4. Now 10 is in there somewhere, so the square root should be somewhere between 3 and 4, and we can play around and try to find what it is. And in fact, when you actually use whatever procedure you can to calculate it, you see that you wind up ultimately with a number that basically goes on forever. So that when you deal with the square root of 10, you usually approximate it to some useful decimal place, depending on the problem you're working on at the time. This type of number is called an irrational number, and we'll see why. For example, here, suppose I wanted the square root to the nearest hundredth. I put my finger on the hundredth place, and I see the digit next to it on the right is a 2, so I just drop everything else. So the square root of 10 to the nearest 100th is 3.16. And we can use this approximate sign, which is a wiggly equal, to mean that it's not exactly right, but good enough. When you have a non-repeating decimal sequence this way, it's called an irrational number, in that it can't be written in the form a over b, where a and b are integers. Remember, numbers written in that form are called rational numbers, that can be expressed as ratios. The square root of 10 is called irrational because it can't be expressed as that kind of a ratio. There is a simple procedure for estimating these square roots called Newton's method. Guess who invented it? Well, sort of like who's buried in Grant's tomb. The point is, you can take the number you want to find the square root of, guess what the square root might be, divide by the guess, average the guess with the quotient, the result you get by the division, and use that as the new guess. And you can get ever and ever closer to the real value of a square root by this process. And there are other processes that are easy to do on computers that will let you get square roots to as many places as you like. I'm not going to bore you with that because there actually is a very nice way of getting square roots using your calculator. You push the square root key and you get it to as many decimal places as the calculator is good for. Let's play around with some examples of finding square roots of numbers with decimals in them. How about the square root of 0.0009? We can do something with this. I can express this as the square root of 0.0001 times 9. Then if you have a square root split this way into factors with no pluses or minuses or anything else in the square root, you can do this. That square root is equivalent to the square root of 0.0001 times the square root of 9. You might ask why I'm doing that. What I've done is split this up into two square roots multiplied by each other, and again I have to stress that if there are pluses or minuses in that square root expression, you can't split it up that way. You only can do it when there are factors, things multiplied or divided by each other. When I do this, I notice that the square root of 9, I know what that is, that's 3. And if I think about the square root of 0.0001, I notice that's also a perfect square, and I can reduce that expression, take those numbers out of the square root to get 0.01 times 3, which is 0.03. Notice an interesting thing here that happens. I see that with multiplication of decimals, the product has more decimal places. The square root, in a way, is going backwards. Notice that has half the number of decimal places as the original quantity that I took the square root of. Sometimes things aren't so simple. If we did the same process with this, I see that, okay, the square root of 9 is going to be 3, but that square root of 0.001 is not something I can do easily. I need to use the calculator, and I can approximate it to 0.032, then times 3, and that's equivalent to 0.096. Going to change topics a little bit now and talk about scientific notation again, and we're going to look at how these division processes follow with scientific notation. And now where we originally in Unit C talked about scientific notation for expressing very big things, we're going to use the same procedures and the same ideas of scientific notation to talk about very small things like hair. You can see all of that I have. Anyway, let's go on, and let's look at a sequence here. You know that we can express 1 as 1 over 1, and we saw that was 10 to the 0. Let's continue this idea down just as we had it going up. If I have 0.1, that's 1 over 10. Let's continue the idea of this exponential form and say 1/10 is 10 to the minus 1. 1/100th is 1 over 10 squared. Let's call that 10 to the minus 2. If we use this kind of notation for smaller and smaller and smaller quantities, That will let us use the same rules we had before in terms of adding exponents and so forth, except now when we deal with small quantities, we can talk about negative exponents. And what that means is 1 over the positive exponent. Let's see how that works. How can we express this in scientific notation? What we need to do is see how many places we have to move now to the right to get to the 3.8, the number between 1 and 10. We move 1 place to the right, we've multiplied by 10 to the minus 1. We move 2 places to the right, 10 to the minus 2, 3, 4, and so we can express that as 3.8 times 10 to the minus 4. How about the diameter of a human hair? Let's start with this, counting places to the right. Minus 1, 2, 3, 4, and we have 6.67 times 10 to the minus 4 for a blonde hair. Turns out black hairs are actually thicker. 1, 2, 3, and we can write this as 2.2 times 10 to the minus 3. Notice that the larger quantity has the smaller negative exponent. Now let's look at dividing monomials using decimals. Remember again what we saw before with the powers of 10 is that if I have 1 over something raised to a power, that's equivalent to that thing to the negative power. For example, 1 over r cubed is equivalent to r to the minus 3. Let's see how that would work here. Again, I can separate out, I see I'm going to have the coefficients 15.2 divided by 7.1. I know how to do that. But now I can express this way, where x to the minus 2 represents that x squared on the bottom. Y to the minus 1 represents that y on the bottom. When I work this out, I can certainly do that math. I get x to the 3 minus 2, y to the 4 minus 1, doing the division of the coefficients. 3 minus 2 is 1, and 4 minus 1 is 3. So I've extended the idea of dealing with monomials to division. We can also talk about the same thing with equation solving, where we divide by decimals. We just do the math exactly as we did before, except we now do decimal math. Anyway.